All right, so this is the end of the redox lesson that we didn't cover in that podcast, just in case you missed class or need to revisit it. And we're starting by taking things just one step farther than what we did in that podcast. We covered in that podcast how to tell when we have elements that are by themselves, their oxidation number is 0, and when we have elements in a compound, the elements' oxidation numbers aren't going to be 0, but we can't see them here because they're canceling each other out. So remember, they always add up to 0, and we give the last element in the compound whatever charge it wants according to the periodic table, and then the first element has to balance it out to make that add up to 0. So P is a -3, which means Al is a +3 here. So we found those oxidation numbers, and then we had started figuring out that if Al is going from a +3 to a 0, its oxidation number is decreasing. That's because it was gaining electrons, more negative stuff, bringing that charge down, meaning that that aluminum is being reduced. And I was telling you to key in on the idea that if that oxidation number is going down, it's being reduced. And if it goes up, like this -3 up to 0, like the phosphorus is, then it's being oxidized. And we're just going to take that one step farther now by actually breaking apart these substances being oxidized and reduced into what we call half reactions. And you see my example up above this first example here, where we took CuS, where we had 0, 0, -2, +2. So our copper was being oxidized because it was going up in charge. And we basically pulled that copper stuff out and separated it into its own separate reaction from the sulfur that was being reduced. Now, we do have some extra electrons here that we're going to add in because that's what's causing these oxidation number changes, the gain or loss of electrons. And remember that Leo the lion says grr, reminds us that losing electrons is oxidation and gaining electrons is reduction. And so keep in mind that when we lose electrons, even though it doesn't necessarily feel right to say plus electrons, notice that these electrons are on the product side. So they've separated out from the copper. So they've been lost from that copper. Before the reaction on the reactant side, those electrons were in the copper, but after the reaction has happened, they're not part of the copper. They've separated out. So chemical reactions never have minus signs in them, except for those charges, of course. They're always pluses. So if we want to show that we're losing electrons, they have to be on the product side. And then reduction, which is gaining electrons, is going to have our electrons on the reactant side. And I love reduction because reduction means going down, which is what we always see with our oxidation numbers for reduction. But also reduction always has the electrons on the reactant side. That double R, reactant, reduction, helps you remember where to put them a little bit better. So reduction, for whatever reason, is just simpler to me than oxidation. So let's go ahead and do that down here with this aluminum and phosphorus example. Since phosphorus was the thing being oxidized, let's pull out all of that phosphorus stuff into this oxidation half reaction, and keep in mind that now that this phosphorus that was with the aluminum is apart from the aluminum, we get to actually see that charge because it's not being canceled out by the aluminum atom. And we're going to move the aluminum down into the reduction half reaction, once again making sure to show that charge, that oxidation number of the aluminum now that it's not canceled out. And that's really our starting point. And I always make sure to put my electron terms on the side that they're going to be on. And then I think, okay, how many electrons does it take? Because it's not always 2, although 2 is a fairly common number. It's generally small numbers, though. But here, keep in mind, in order for a -3 phosphorus to turn into a regular old phosphorus, it's going to have to lose those 3 extra electrons that were putting it over being neutral, those 3 negative electrons that was making us a -3 charge. And this aluminum plus 3, in order to turn into normal aluminum, would have to add 3 electrons in, gain 3 electrons. And so we are going to put those electrons on the reactant side for reduction. And in the next part of this process, because we are going to add some more steps to this process, we're not going to be doing the breaking apart and electron steps at the exact same time. They're going to be a little bit farther separate. And the words we're going to use for it is that we're going to balance charges by adding electrons. And that sounds weird, but if you think about balancing is about making things equal on either side of our arrow, notice how the total charge here, the 3 negative electrons and that positive 3 charge together add up to 0, which is equal to what the charge is on the other side. Now, it's not always going to be this simple. Like, oh, it's a +3 charge here, so it's 3 electrons. There could be some times when maybe aluminum's going from a +3 to a +2 instead of +3 to 0. So in that situation, if I have a +3 charge and I'm just trying to make it equal, bring it down to a +2 charge to balance my charges, then that would only need 1 electron. So we're going to get to that more complicated stuff in a little bit. For this half reaction, it's just like this. Now, another quick note is that if I were to ask you, and this isn't something I'm going to ask you on the test, but in general, keep in mind that there's only 3 electrons being transferred here. Don't think of these electrons as different than those electrons. Remember, these are half reactions. They're both half of this whole reaction. These are the same 3 electrons. These electrons that are being lost from the phosphorus are the same electrons being gained by the aluminum. And normally that happens all at once. The phosphorus gives them straight to the aluminum. But because we're pulling this apart here, we can see that kind of losing and gaining happening separately. And that's going to be important for our redox reactions because they have to be the same. Because just like atoms, we can't have any magically disappearing electrons or magically appearing electrons. The number of electrons lost have to be equal to the number of electrons gained. And here in our simplest example, they are. But in the next more complicated examples that we do on the next page, they're not always going to be equal. So we're going to have to make them equal in order to get this balanced. And that's one of the special things that can happen in a redox reaction. But let's start by finishing up this page, looking at this next reaction that we're going to pull into halves. And I know it might look a little bit weird. This is not a reaction that you would normally see in balance normally, but this is actually pretty common for redox reactions and redox situations where you have all of your elements separate. And don't let that confuse you or intimidate you because it actually makes finding your oxidation numbers easier. Remember, any lone element that doesn't have any charge written on it has 0 as its oxidation number. And if it has a charge written on it, then that charge is the oxidation number. So you almost don't have to think about these oxidation numbers when they're not in compounds. If they're by themselves, even if it's a diatomic element, if it's by itself, it's either 0 if you don't see a charge, or the charge is the oxidation number if we do see one. And if we track these changes, zinc is going from 0 to +2. It's going up in oxidation number, so that's being oxidized. And our copper is going down from +2 to 0, so that is being reduced. Always good to double check that, but once we knew zinc was being oxidized, copper was probably being reduced. So we're going to pull all of that zinc stuff out into our oxidation half reaction, and all of that copper stuff out into our reduction half reaction. And now we just need to add electrons, and these are still the simplest situations where these are actually equal. To go from 0 to +2, this zinc would have to lose 2 electrons. To go from +2 to 0, this copper would have to gain 2 electrons. So these are equal, which is good. It makes things simpler, but it's not always going to be quite that simpler. But let's go ahead and look at the next page and see what is going to make this process more complicated, because it does get a little bit worse, but it's not quite as bad as it first seems when you turn the page and you see this 8-step process. I know that looks pretty scary, but if you read the little blurb you do up at the top of the page, this really is just kind of a 4-step process with some little details in each step we need to pay attention to. That first step, and I did purposely make a little space in those 8 steps between these big chunks. The first step is to separate the reaction into half reactions. Okay, we just practiced doing it. That's not too bad. Just check oxidation numbers, then pull the elements apart. And we're going to do that in order to help balance our atoms and our charges separately. So that's what's special about these redox reactions, is those electrons, and we will see those electrons and have to balance them a little bit in the long run, but that's not honestly that bad. And then the last 2 steps are just about squishing those half reactions back together into what we call the overall reaction, and then double checking what we've done. So even that step 8 is just kind of extra. It's not really its own step you have to do, but I would recommend when you're done, you kind of do a quick double check, make sure you didn't make any mistakes. So we separate things, balance atoms, charges, and put them back together. And like I said, we just practice separating them. That's not that bad on its own. When we balance atoms, though, there are some specific atoms we need to pay attention to first versus last. And it's really important that we do focus first on just the elements being oxidized and reduced. And then if there are any oxygens or hydrogens, we balance those next. And that's kind of like normal balancing. The thing that's going to be a little bit different than normal balancing is that here, when we're balancing our oxygens and hydrogens, we're actually going to be adding some completely new substances, H2O and H+. And I recommend, I'm always going to write that as H+1, because that helps me see those charges that we're going to be balancing in this next part. So you might want to make that little change there, add a little 1, but it's up to you. And because we're going to balance some things in a weird way by adding new substances like those electrons, water, H+, I think it's worth writing down here that in step 2, when we're balancing those special elements that are being oxidized and reduced, we just use coefficients. Just kind of like normal. Put a number in front of one side or the other in order to get the atoms equal. And then keep in mind that, like the 2 reactions we saw in the last page that we pulled apart, there were no oxygens in there. And that actually means that we can skip over steps 3 and 4 together if there's no oxygen in the reaction. So we're going to learn along the way, and you're going to see in these examples at the bottom of the page, that oxygen makes things more complicated, and the easiest problems are the ones with no oxygen. Now, we've practiced adding electrons. It might be worth writing LEO-GR here, reminding you losing electrons is oxidation, gaining is reduction. Or you could even just write oxidation electrons on product side and reduction electrons on reactant side. Anything that you need in order to help you remember that those will always be on the same side of the reaction. And I always just start by writing an electron at a time on that side and then asking myself, how many do I need in order to balance that charge? But those will always be on the same sides: oxidation, product, reduction, reactant. And then the final step seems kind of complicated about adding half reactions and canceling substances that are on opposite sides, but really the only thing you're going to have to worry about canceling at this level is electrons. And they will always cancel because they're going to be on opposite sides and they're going to be equal. So they're just basically going to disappear, and then we're going to just squish everything back together again. So we'll do that, and I think you'll see how much easier this process is in practice than it is on paper, because this looks like a lot, and when you see these examples it looks crazy, but it really isn't that bad. So let's look at this first example. If I want to start by splitting my reaction into half reactions, then I need to find my oxidation numbers of all of these elements. And just like the last one that we did, these are pretty obvious because each of our elements here are by themselves, but I like to go through that process just to double check. Here I see my zinc is going from 0 to +2. That means it's being oxidized. So I'm going to pull all my zinc stuff into that oxidation half reaction. And if I double check, yes, hydrogen is going from +1 to 0. That is going down. So our hydrogen is being reduced. So notice, because I don't have a little separate space to commit to which one's being which, I wrote it down off to the side. You don't have to, but that helps make sure we don't make any silly mistakes. And as I am pulling all of that zinc stuff out into this first line, I want to recommend that you start kind of more in the middle. You saw I was kind of running out of space for some of my electrons when I was adding them before. So if I start in the middle, that makes sure I have space on either side for whatever I need to add. The other thing is I try and make sure to line up my oxidation and reduction half reactions, just because that's going to make the adding up process easier at the end. So I've split my reaction into half reactions, and now let's go ahead and balance those special elements, just our zinc and hydrogen here. And don't let the charges fool you. I have one zinc here and one zinc there. This +2 charge is not the number of zinc atoms, that's the charge. And we're going to balance that with electrons later on. But number of zincs is equal, so there's nothing to change here so far. On a reduction half reaction, though, I have 1 hydrogen on the reactant side and 2 on the product side. So we do need to balance that. And I'm going to do so by putting a coefficient 2, up in front of the side that just has 1. So next, if we had oxygens, we would need to balance our oxygens by adding some water. But there's no oxygens here. So we get to skip both of these steps. And instead, we're going to jump into the electron steps. And so we're going to add electrons to our oxidation and reduction reactions. And I know oxidation, it's on the product side. And if I'm thinking, okay, how many electrons do I need to add over here to match the charge I currently have on the other side? Well, the other side is 0, and I currently have a +2 charge here. So that's going to be 2 electrons. Down in our reduction half reaction, we need to put our electrons on the reactant side. And once again, if I'm trying to think, how many electrons do I need to add here to bring my total charge on that reactant side down to match the total charge on my product side? Well, the product side is 0, and here I have 2 +1s. Don't let the +1 fool you. If I have 2 H +1s together, that is a +2 charge. So here, once again, I am going to need 2 electrons in order to balance my charges. Now at this point, we have added our electrons, and the next step says to multiply by some integer to make the electrons lost equal to the electrons gained. Well, they're already equal. 2 electrons, 2 electrons. So we don't really have to do anything there. We always should check, but there's no changes to make to the reaction if they're already equal. So now at this point, we want to cancel any substances that are the same on opposite sides, and electrons always cancel. There's nothing else that's identical on both sides. And so now we're just going to add these back up, which means taking everything that is on the reactant side from both half reactions and bringing it down onto the reactant side of our overall, and then taking everything that's on the product side of our 2 separate half reactions and bringing it down onto the product side of the overall. And it doesn't matter what order these are written in. I could have written this 2H +1 plus Zn, as long as both of those things make it down into the overall. You're just going to see me start top to bottom, left to right, just, how we read in order to do that in an organized fashion. But this is our final answer. It really isn't that hard to do. The electron step is probably the weirdest step, but in these simplest cases, sometimes it's really not that bad. Now, I am going to post the next couple of examples and work those out. I want to point out that this next one has a little bit of oxygen in it, which is going to add to some of the steps we need to do. This last one here has a lot of oxygen in it, and the process is going to be a little bit more involved because of that. So in general, I will allow you to skip this problem completely. If you want to watch me work it out, I have posted the video and you can do that, but I'm never going to give you a problem quite at this level to do in honors. But I do want you to try number 4. I am going to post the answers to it as well. But I want you to try this one after you've watched at least one video that has an oxygen example in it. Try that one, see where you get stuck, and then watch the video and see if I can help get you unstuck. Because if I can't just with that video, then I want to work with you more one-on-one in class about that, and maybe work that example for you and with you in class again. But keep in mind that over everything, oxygen makes things more complicated, and on your test, you're only going, in order to make a 100 on your test, you're just going to be given a non-oxygen example. You will have the choice to choose between that non-oxygen example or an oxygen example, and the oxygen example could get you some bonus points if you do it correctly. So the minimum that I need is you to be able to work out a non-oxygen example to get a 100 on this test. So if that's the level you're at, if this made sense, maybe just go try some other non-oxygen examples in your packet for right now. Just make sure you can get to that 100 level, and then maybe consider watching an oxygen example and seeing how it's different and more complicated.